Okay, hello everybody. Welcome to chapter 3 of Test and Measurement. Okay, and so today we will be talking about the exciting world of reliability. Woohoo! Woo! Woo! All right, so let's begin. Let me call up my screen here. And alrighty then, why don't we start? So, reliability. You guys have probably heard this concept before in intro psych, stats, and so on. We will get into reliability in great depth, probably far greater than you would prefer. And we will also discuss it as it applies to test and measurements. Okay? To start us off, some initial points. First of all, just what is reliability in general? Yeah, you can think of reliability as a measure or index of how consistent measurements are. Yeah, so a thermometer is pretty reliable, right? If you're not sick, it takes your temperature, and your temperature, let's just say at 9 in the morning, will be pretty consistent or similar to your temperature at 10 in the morning. All right, there might actually be a degree or two variation, but it's fairly consistent. Okay. Same thing goes with psychological measures. Yeah, with many things. Let's just say you're measuring, let's see, someone's personality, and you're measuring them on introversion, extroversion, and that's fairly consistent over time, right? You measure them at age 16, and they're introverted, and then you measure them at age 25. Odds are their score is not going to be that different. There may again be some variation, right? But that personality continuum, introversion versus extroversion, not unlike temperature, it doesn't change all that much. Alrighty, maybe due to certain circumstances, just like temperature, but not a whole lot. Now, just because scores are reliable, yeah, on a instrument, on a test, it doesn't mean that what you're measuring is valid. Yeah. Now, validity, we'll get into in the next chapter, refers to whether you're measuring the construct of interest. All right, whether you're measuring what you're really intending to measure. Okay, now we know a thermometer measures temperature, right? But a test, psychological test that purports to measure a personality construct, it may, right, depending on how well it's validated, or it may not. Yeah, a test that purports to measure introversion, extroversion across time might have high reliability, but it may actually not have strong validity. It may have weak validity in that you're not actually measuring introversion, extroversion, but you're measuring something else like conscientiousness or emotional stability or something else. Yeah, we'll get into how you determine validity in our next chapter. Okay. That said, though, if your test had strong validity, and we'll find out how you can show that, okay, it's also going to be reliable. Yeah, because if you're accurately measuring something, right? If you're really seeing temperature, if you're really seeing extroversion, introversion, yeah, multiple measures will show relative consistency. All righty. Now, the thing that what reliability isn't related to, yeah, it isn't related to actual real changes. Okay. So let's just say with the thermometer, right? It's 90.6 one day. Then a week later, you catch a cold and you have a fever, and it measures it at 102. Does that mean that the thermometer is not reliable? No, it's very well a reliable instrument. Yeah, um, because of the difference, even though they're inconsistent, it's relating to a real change, what that darn thermometer is supposed to be measuring. Okay, so real changes do not go to reliability, alrighty, or unreliability. Okay, what reliability is concerned with, okay, is unsystematic errors. Okay, I'm sorry, systematic errors. Okay, um, I'm sorry. unsystematic errors, stuff that's not planned, that like you didn't plan to get a code, or let's just say the person, right, whose personality is generally introverted, right before being measured on the psychological test, had a really happy, encouraging moment seeing an old friend. So, and on top of it, they got a good rest, so they're super excited right before they take your measure, right? So they're excited that day. They are good rest. They have a lot of energy. They just saw an old friend an hour ago. So they're kind of socialized, right? They're kind of thinking in terms of making connections and stuff. And when you ask them questions about their personality, right, they might answer more in line with the situation, right, that morning and seeing the friend, and so on. Alrighty, so that wasn't planned. The code wasn't planned. It's all this kind of error, right? Unplanned stuff, unsystematic errors that reliability measures. Okay, so it's that error that we're kind of concerned about there with reliability. Okay, not constant error. Okay, so constant error may be like the individual's language that they speak, right? And how they interpret the questions on your exam. Alrighty. Now that's going to be fairly constant, right? The language they speak and so on. Yeah. And how they understand the items, relatively speaking, right? That is not what reliability goes to. It goes to the unsystematic error. All right, woohoo, stats review. So we're gonna be doing a little bit of stats review, nothing too heavy duty, okay? But necessary. So for our purposes, we're gonna be looking at the statistical ideas related to correlation index, okay? Now, when thinking about correlation, yeah, and we're gonna be just looking at correlating 2 points of data, all righty? And that's what reliability is about, right? A test at one point and a test at another point in time. That kind of data will be mapped out on, if you were to see a scatter plot of it, yeah, the kind of scattergram or scatter plot you would have would be a bivariate distribution, yeah, X on the horizontal and Y on the vertical. All right, so the scores at testing point 1 and the score on testing point 2. All righty, if we're talking about reliability and 2 points of time. All right. Now, correlation coefficient, yeah, is designated by the index R. All righty, and the most common correlation you'll see related to tests and measurements is the Pearson product moment correlation. As you may recall from previous classes like research methods, abnormal site perhaps, I know I touch on it very quickly. The value of a correlation, right, is that it tells you the correlationship between two variables. Yeah. So if you know the scores on one variable, variable A, and the scores on variable B and how they relate or correlate, yeah, what that allows you to do is that it allows you to make a prediction. Yeah. And if you're talking about 2 points in time, let's just say taking the SAT and then first year freshman grades, GPA, those two scores and their correlation, right? It allows you to make a prediction such that if you have some SAT score, you can predict, not absolutely, but with a reasonable degree of probability, what their first year GPA score is going to be. Okay, so that's really powerful. And that's the magic or the power of a psychological test. Yeah, whether it's IQ, SAT, personality, or so on, is that it allows you to predict something in the future. Alrighty. Not that the first thing causes the latest thing, right? Not that the whatever you measured at point A causes B. It's not saying that, right? Correlation is not causation. But it is saying that this first thing, the score, allows you to make a prediction of what the second thing is going to be like, which is huge, right? Very valuable in you know, multiple situations. Now, the relationship that if things are correlated is linear in nature. Yeah. In other words, the way X on the horizontal relates with the Y. Yeah. If they're correlated, there'll be the relationship is described as linear in nature, meaning that if you were to plot one point for someone's score on X and then someone's score on Y, and then you'd see exactly where their score is. We'll look at a couple nice graphs and illustrations as opposed to my waving my finger in the air. And you scored that for a sample of subjects, right? If the X and Y are correlated, all of those points on the graph will kind of form a line, or you could draw a line that kind of explains the relationship between the scores. Okay? But be rest assured, not all relationships are linear. They may be significant, but they may not be linear in nature. Okay? Or they may have no, and if they're not correlated, it's just going to be a bunch of dots on the graph for the most part. Now, there are different classes of correlations. Most of these you're well familiar with, but let's review it so that we're all kind of on the same page. The first is a positive correlation. Okay? A positive correlation concerns the relationship when two variables are related in the same direction. Yeah, in other words, when A goes up, B probably goes up, and when A goes down, B goes down. Okay. Now, what's a common positive correlation? Positive correlation, very consistently found in dozens and dozens of studies, the correlation between anxiety and depression. Yeah. Depressed people, right, will have a high depression score. And if they take an anxiety score, lo and behold, their anxiety scores tend to be on the high side, and vice versa. People who aren't depressed also will show low on anxiety. Yeah, the two are very correlated. Yeah, and decades ago, there was such a large degree of consistency found. It was thought that it may behoove psychology and psychiatry to come up with a construct which actually captures depression, anxiety. Not like Einstein's time-space, but the idea that these two constructs overlap so much that it's maybe better to describe that construct as depression hyphen anxiety as opposed to trying to separate the two. Okay, so when things are positively correlated, and if the relationship is graphed, they will show a linear relationship, like kind of like what we got here. Okay, going that way. And let me see if I can, oh, here we go. Let me just. Okay, so you'll find a linear relationship like this, yeah? So here as hours of studies increases, right? Scores on the exam also increases. Okay, no big surprise. So we see a co-relationship like that. Alrighty. Now, oops. Now, in a negative correlation, what you have is a relationship that's inverse in nature. Yeah, meaning that when one score goes up, the other goes down, and vice versa. Alrighty, and a classic example of that is with let's say the relationship between self-esteem and depression. Again, tons of studies tend to support that. That people who tend to have high self-esteem scores tend to be low on depression. Yeah, people feel good about themselves tend to be low on depression. Big surprise there, right? And vice versa. People who are low on self-esteem will have high depression scores. Alrighty, and this is the way it typically will show itself. Okay. Now, when there's no relationship between the two, yeah, variables, you'll get a bunch of scores, right? If you try to plot order of completion of a task with test scores, it doesn't matter, right? There's no relationship. You get a bunch of plotted scores that look like this. Okay, that just seems to be like a mist, a cloud with nothing bunching up. Alrighty. Now, if they were aside from a zero relationship, when there is a relationship, you can also determine the strength of that relationship in terms of the absolute value of the correlationship. Yeah. And that's the number that follows the index. Okay. So here we see the value 0.86, which indicates a strong correlation. Now, what you would describe as a low, moderate, or high correlation kind of depends on the situation, the context. But as a general rule, you can think of correlations as operating along a kind of rule of thirds, in that very typically correlations between 0.1 and 0.3 are described as low. 0.4 to 0.6 is moderate, and 0.7 to 0.9, you rarely get a perfect correlation of 1.00 are described as strong correlations. Okay, low, moderate, and high as a general matter. Okay, so alrighty, as we mentioned before, the most common type, there are a number of different correlation formula. Alrighty, but the one we're going to be focused in on is the Pearson product moment correlation, or Pearson R. Now, what the Pearson R represents is a relationship of one variable. Well, we have two variables, right? We'll call one X, the other Y. We can say like depression is X and Y is anxiety. Alrighty? And R represents the function of the moment, okay, or potency of the Z-score products. Now, what does that mean? Okay, well, let's flesh this out a little further. Okay, what we're looking at is the mean of the Z-score products for X and Y. Okay, whatever. What do you mean now, Shima? Let's go a little further. Okay, now look at this definitional formula. The Pearson R is equal to, right? You recognize the Z-score for X, right? Let's say someone's depression score, and the Z-score for the anxiety score, right? Multiply, right, the product of X and Y, right, for subject one, then do that for subject two, and so on until you get to the nth subject, yeah, whatever that's 10 or 20, whatever this n is, okay? Add that up, divide it by the total number, right, 10 or 20 subjects, and that will give you the Pearson R. It is, right, and if you look at it, it kind of looks like a mathematical average, right? So we're getting the sum of the Z-score products, right, for all the subjects divided by n. Looks kind of like the variance too, yeah, oddly enough. Now, what does that give you? Well, kind of like variance, right? But in this case, instead of looking at, whereas with variance, right, we looked at each subject score against the mean, right? And in that situation, variance was like, and we squared that, right? So we could see what was happening. We could see the variation of each person's score against the mean. So that's the sum of X minus mean times X minus mean. Okay, so we could see something, as you may recall, right? But with covariance, we're looking at two different deviations. X minus the mean from that mean for all the X scores, right? So each depression score minus the mean of all the depression scores in that sample times Y minus the mean for Y, right, the anxiety score, minus the mean of all the anxiety scores for that group. Okay, and similarly, like the variance of formula divided by n minus 1. All right. So what this does is that it allows us to see the variation between X and Y, not just between the variation in X, right? But for all the X's against the mean. But here, the variation of X against its mean, Y against its mean, and the product of the two. So to see how they correlate, okay? To eventually see how they correlate. Now, the next thing we do is a process of standardization of that score. Okay, so initially we started with the z-scores of X and z-scores of Y. Alrighty. Now, in order to standardize the covariance, what we do is we take that COV XY, right, covariance of XY, and we standardize it by dividing it by the standard deviation of the X scores for that group times the standard deviation of the Y scores for that group, okay? And once we get that product, then we divide the covariance by that product, right? Divide the covariance by that product. Okay, let me Oops, sorry about that. Just trying to, okay, there we go. Trying to get this again here. Okay, so here we got the product of the standard deviation of x times the standard deviation of y, dividing into the covariance of xy. And now you standardize, right, R. And what that allows you to do, yeah, it now allows you to compare the covariance of x and y, or now what we have is Pearson correlation with other Pearson correlations. Okay, because it's important in terms of interpreting what that test means with respect to other tests, what that test means with respect to research findings. Okay, other research findings. So we'll get into that a little later. Okay, so let us move. And here we've moved. All righty. So in order to determine the values, let me try to move my box here a bit. Oh, my box is fine. We need to determine the values of x and y. All righty. So to do that, we have the formula here. And, okay, so here's the formula, the computational formula. Yeah? Before we looked at the definitional formula, kind of the conceptual formula. So you understand what variables are involved and what you're doing with the variables. You have to compute the correlation. Here's the computational, the actual values that you kind of insert. Okay, it's the same thing, but written up in a way that now you can, with paper and pencil or a calculator, compute it. All righty. Now, let me get out here. So what you need to do is you need to know the number of subjects, the sum of all the x and y's, right? We'll look at that in a moment. The sum of x, sum of y, sum of all the x squares, and sum of the y squares. Sounds like a lot, but it's really straightforward and fairly simple. Alrighty, but it looks like a big old mess. But that's part of doing math, is looking at something that looks like a big old mess and kind of simplifying it. Okay, so what you want to, so the only new term really is sum of xy. If you've done this is going to be kind of the unique thing. Everything else is going to be fairly straightforward. That's probably the one that involves the most work, or that's why it says the only new term. All righty, so in this situation, let me annotate again. Okay, so what you're going to do is you're going to get a bunch of subjects, A through N, and here are their scores, their heights. Okay, the next thing is an interesting little correlation, is we're trying to see what the correlation is between people's height and how much moolah, how much money they make. All righty, do taller people make more money? And I sure hope that ain't the case, being a shorter guy. But that's a study that they're doing right here. Okay, what you can see I underlined in red are the values you need to find. So you need to find the sum of x, right? You add up all the heights. Okay, here's the sum of x squared. So it's taking every x score, squaring it, then adding it. Okay. Then you find out what the salary is, right? That's 47,000, right? Annually, we hope. It's probably 47,000 annually versus 33,000. Add it up, square it, add that up. And finally, right, here's the new thing. You got to multiply each x times y, and then you get its product, right? Same here, 74 times 45.5, get that. Then you add it up. Then once you get these 5 values, you simply insert it into the Pearson formula. Okay, bing, 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 bang. Got to be careful, right? Simple, but careful, right? You got to be sure you insert the proper value into each part of the formula. And, just follow simple math, simple algebra, right? Start in and then work out, right? So multiply n times that, and then these two and then, right, do the subtraction. So this inner stuff and then go outwards, right? Same thing here. Multiply n times that, the square that, then, subtract this from that, okay? Do the same here, multiply, and then get the square root, and then divide the numerator by the denominator. All righty? In and outwards. Think of it that way. All righty. Oops. Get out of here. Now, the other thing you do once you calculate the correlation is you want to find out whether it's statistically significant. Now, when you do this on SPSS, it'll tell you, all righty? But it's important to kind of understand old school style, how you would have done it. And we're going to actually do the old school style in an exercise later, later in the program, all righty? But here's the way you would do it. You would use a table of critical values. Now, critical values means kind of like the threshold you have to surpass, the value you need to exceed. Your correlation is a value, right? It'll say correlation 0.86. Does that value surpass the critical value or cutoff? Okay, is it higher than the critical value? So how do you determine what the critical value is? Okay, well, you got to determine what the degrees of freedom for your test is. Now, the degrees of freedom, right? Here you determine it by the number of subjects minus 2. So in our case, I think there were 11, something like that. Minus 2 is 9. So you go to 9. Right? Number of pairs of 9 is right. 9 subjects, so 9 pairs of scores. Originally 11 minus 2 becomes 9. So you look here, right? Degrees of freedom 9, and that's your cutoff for a probability of 0.05, and your cutoff for a probability of 0.01. Okay. Now, what does 0.05 and 0.01 mean? Okay. As you may recall from stats, yeah, it refers to the probability that what you found is a chance event, random, yeah, versus something that's not chance, yeah, that is, in other words, there's something going on here. The probability, the odds are there's something going on here. It's not a random chance happenstance, okay? So again, 9, and you can see the cutoff for 0.05. So there's a 5% chance that this is a random event. 0.86 exceeds 0.602, so it's significant at 0.05. And is this significant at 0.01? Yes, it is. It's 0.86, exceeds 0.75. So you know you're statistically significant at the 0.01 level as well. Okay. Now using the same, now let's just say instead of 0.06, you found 0.62. Yeah. Well, you would have been significant at 0.05, but not at 0.01. Okay. Now, does that mean you found statistical significance? Yes, but you got to say to what degree, at what alpha level, what probability level. And here the alpha probability level, yeah, is 0.05. You found because your correlation was 0.62, it exceeded. In other words, the co-relationship in terms of what you found quantitatively, right, exceeds the cutoff at 0.05, a probability of 0.05. It exceeds this cutoff of 0.60, but it doesn't exceed 0.73, which is the cutoff for 0.01. All righty, so that's that. And there's yet another thing you can do with this correlation value, this R you found, right? And it's the coefficient of determination. Now, the coefficient of determination is simply, you're taking the R value and squaring it, okay? When you square that value, okay, like let's just say you square 0.86 and you get a certain value, that value you can kind of treat as a percentage. All righty. And what that percentage tells you is how much of the variance in B is accounted for by A. Yeah? It doesn't mean how much B is caused by A, but how much A accounts for, explains the variance in B. All righty. So you just take the R and you square it. All right. So moving right along. Okay, the next thing, well, we're not going to do the next thing here. We're going to do the next thing in our face-to-face meeting. All righty, face-to-face or Zoom meeting, depending on how we're handling things. So we will skip that, but what we will be doing in that meeting will be actually working on a Pearson by hand, but by way of competition. All righty. So that's kind of just bypass that. Very good. So that's a review. That's our stats review. Woohoo! It's all over. Well, not completely, but pretty much over. And you will do a Pearson product correlation at another meeting. All righty. So with that, let's continue our discussion about what a linear relationship tells us. Okay. Now, a linear relationship can be expressed in terms of a mathematical equation. That mathematical equation is a linear regression. All righty. Linear regression equation. Now, you may recall this from maybe from stats, research methods, perhaps, or a math class, right? This is the relationship. This is the formula for linear regression equation. Yeah. So in order to figure out y, predict a score, it is equal to the slope of the line times the score plus a, or the y-intercept. Yeah. So let's flesh that out a little further. So if we look at this line, yeah, if you were given x, you could predict y, but you would need this formula. And in particular, you would need b and a. You would need to know the slope, or the angle of the line, plus a, where this line intersects with y. It's called the y-intercept, or where the line intersects the y-axis. Okay, so you get that value plus the slope. And you may recall from other math classes, yeah, the slope is simply the rise over the run, rise over run. So let's just say the rise here, let's just say you make a triangle, and the rise, let's just say for our example, for our discussion, is 4. Rise over the run. And the run, right? So the length, so the rise, the length of the vertical here on the triangle is 4. And then the length here of the width, the run is 2. 4 over 2, the slope would be 2. Okay? Now the other, so if you have the slope and the y-intercept, now you can predict y based on having x, which is kind of cool. All right, this is your little prediction machine, so to speak. Now, the other way to think about the linear regression equation, or the line here, that's what the line represents, this equation. It's the line that best kind of represents all the scores. All righty, it's kind of like the middle person between all the scores. And it's this line which produces the smallest distance among all the scores. Yeah. So this line has this distance, that distance, a little longer distance here, here. But it's the one that would produce, and if you sum that up, this line would result in the smallest total, as opposed to if a line went that way or a line went that way. It's the one that's closest to all the dots on the graph. Okay, another way to think about the linear regression line, yeah, is here's a line and here's a bunch of scores, just like the other one, similar, right? Different graph, but it's the same idea. All righty. Another way to think about these scores is that they have a certain degree of scatter along the line. Yeah, so the scores are scattered. At this point in the line, the scores demonstrate a certain degree of scatter. At this point, they have, right, wider scatter, even wider scatter here. But then at this point, right, the scatter is less. It seems to be kind of bunched up more. Okay. Now, one of the things that's with a correlation, yeah, an assumption underlying, when you know that something's correlated, right, underlying assumption is that the way the scores are kind of bunched up at each point, right, is normally distributed. So let's look at 20. Okay, we look at 20 here, and let's just say you imagine kind of flopping this table right onto the y-axis. Okay, taking it and go boop like that. And then, so in other words, so that the bell-shaped curve here is now, what do you call, upwards, okay? So flipping it right here so that it's standing upright, okay? The idea would be that these scores are normally distributed, kind of making a bell-shaped curve. Yeah, you can kind of see that there, all righty? So if they're bunched up, at each point, they're going to be kind of bell-shaped like this, okay? Now, this is going to relate to a concept called the standard error of estimate. Yeah, think of the acronym SEE, right? Standard, where is that? Standard SEE, standard error of estimate. And think of it as seeing into the future or predicting the future. All righty, we're going to get back to this. And this notion of how the scores are normally distributed allows us to see into the future. All righty, let's stop here for a moment. Hi, welcome back. Just took a brief Red Bull break with you. So moving right along, let's get back to the PowerPoint slide. And oh, here we go. Oops, sorry about that delay. So here we go. Continuing our discussion, let's talk about things that can affect the correlation coefficient. Okay. Now, so what can increase or decrease the absolute value of R, or the size of the correlation coefficient? Well, let's talk about three factors. The first is, as you may recall, essentially what we're looking at is a linear relationship. Yeah. So number one factor will be the degree to which the linearity, the degree of linearity versus non-linearity in the relationship between the two scores. Yeah. If the two scores are not linear, all righty. Now, what other kinds of relationships could they be? They could be curvilinear, yeah, where it's instead of a line going that way, or the scores bunching up in like a cloud, in a cumulus cloud, yeah, going in a certain direction. The relationship would be curvilinear. You know, let me show it that way, curvilinear. And the extent to which the relationship is nonlinear, like in a curvilinear relationship, right, or there's two, it's bimodal, right? The Pearson will underestimate the relationship. It won't be able to estimate it well. And if anything, it will underestimate the actual relationship. Okay. The other notion is homoscedasticity or heteroscedasticity. Now, what does that mean? Sounds, by the way, this is a term, if you want to sound fancy schmancy and show off to your friends, I would drop this term, homoscedasticity or heteroscedasticity. Quite fancy sounding. But basically what it relates to is that normal distribution of scores along the line on the scattergram. Okay, scatter plot, scattergram. Yeah, I think you can say scattergram, right? So that normal distribution, right? That if it looks like somewhat like a normal distribution, right? It might vary. It might be more tightly distributed and more loosely distributed and tightly distributed again. But as long as, to the extent to which it looks like a bell-shaped curve, you have homoscedasticity, all right? Or they're similar, they're bunching up in a way, in a fashion. If they're not, if they're all super varied, right, and you can't see a bell-shaped curve, it's heteroscedastic. You have more heteroscedasticity, okay? And with greater homogeneity, you have a higher correlation, and vice versa. Now, the other thing really that will affect correlation coefficient will be the homogeneity of the subjects, all righty? Now, when the subjects are very similar, right, correlations tend to be lower. But when subjects are heterogeneous, the correlation tends to increase, right? Or it may actually inflate the score. yeah, versus homogeneity, which will have a deflated score. Now, what will kind of illustrate that nicely? Well, here's um, illustration, right? I believe this is in your text, right? Of a group of scores, right? Now, let's imagine on the X that we're talking about SAT scores, right? So low to high SAT scores versus low to high first year GPA. Alrighty. Now let's also think that think of the squares as you know groups of students. So A is everybody, B are the slightly better students, and the C are the honor students. Alrighty. Um, let's see. Um, well, no, let's just think of what do you call them? I'm sorry, not honor students, but just think A, B, these groups of students are more similar, and then these students right here are super similar on, right, this, this is a whole university, this is a subgroup B of the university, right, which have 5 things in common, and this is a subgroup of the university which have 10 things in common, all righty? And if these are the scores, their performance, for example, on the SAT, right? You can see that if we get everybody, right, you get a line or a cumulus cloud, right, that bunches up because we got a variety of people on their low and high scores, righty? But if you were to just get this group, right, or far more similar, it's harder to see that line. It just looks more like a scatter scores. Yeah. But because you've got a wide range of people who do super well, not so swell on the SAT, and super swell on the SAT, yeah, and those same people probably didn't do so, probably, not absolutely, didn't do so well in the first year of of their freshman year, and they did really well, right? It's easier to see, right, the scores kind of shaping up along a line, all righty? And it's because of that greater heterogeneity variation, it kind of like yanks out the relationship of the score of the relationship between X and Y a little further. All right, yanks it, kind of an awful way to describe it, but works for me. Okay, now what are some things that contribute? We're getting away from Pearson and correlations. Let's just look at look at reliability. As we mentioned before, it is a measure of the unsystematic error. Yeah, so we want to know how much it can vary, right? We want high reliability, right? So that the idea is that it's fairly consistent. Okay, if it's really variable, then it's going to be harder to get that temperature. It's going to be harder to see that personality construct. Okay. Now, things that can contribute to lowering reliability will be the extent to which the test is scored based on rater judgment. Right? To the extent the scores can really vary based on the judge's arbitrary decision making, or they have a lot of um, room to make a determination. Yeah? It's going to undercut reliability. But the extent to which scoring is very structured, and the person who's doing the scoring, right, has to really stick with the rules, right? And if they get a certain response, they have to score it a certain way, right? So there's low rater judgment that's going to make the test more reliable. Right? Think of it as the source of scoring is more structured, more controlled. The greater control and structure you have, the less error is going to enter the picture. But the more you leave it up to people who go, oh, that's a high score, that's a low score, based on their own arbitrary decision making, right? Now there's error entering into the test, the person's own arbitrary decision making. Another thing that can contribute to reliability, or contribute to reducing reliability, concerns the test content. Yeah, and the test content. We'll get into this a little further. Yeah, what is the test content? But generally, for now, it suffices to really think about that as the nature of the items, okay, the questions, how they're worded, and so on. Yeah, to the extent there's lack of clarity, lack of in terms of what the question is asking. Yeah, could it pull out different responses from different examinees or from the same examinee but at different times because it's not clearly worded? that's going to introduce error, right, into what you're trying to measure. All righty. This deals with not necessarily the test, but how the test is scored, right? So outside of the test, this is dealing with the test itself. How is it worded? How is it drafted? And so on. Now, outside of the test is test administration. Is it given consistently? Yeah, like the SAT, if it's given consistently, right, and they have very strict rules about how you administer the SAT, that will increase reliability. But the extent to which someone has, can arbitrarily determine how long the test is going to run, how you give instructions, whether and all that kind of stuff, right? You add error to the test. Right? And finally, to the test, right, not the test itself, will be the personal conditions, right? Temporary conditions of the examinees. If they're hungry, if they're in pain, if they're anxious, all that kind of stuff, right? And which you always have to anticipate, yeah, with a test can happen. All righty. But that being said, that can contribute to reliability. Let's talk about true score theory. All right. Now, the idea underlying true score theory is that when you're measuring something, okay, be it a temperature or personality or IQ or what have you, the idea is that there's this desired absolute true score. Okay, we know that this is it. This is your intelligence. This is your personality. This is your internal temperature, and so on. Now, what classical test theory posits, yeah, is the idea that in any observed score, the temperature and the thermometer, the score on the personality test, yeah, includes the theoretical sought after true score. But the reality is that there's always going to be error. All righty. So what your score, right, that number, be it a raw score, standardized score, is actually a measure of is the sought after theoretical true score plus error. Yeah. And now the true score would be if we could take out all unreliability, all unsystematic error, which we know that's not really possible, right? But that being said, it's important to understand what a score means, yeah, and what we're really gunning for, and trying to remove as much unreliability as you can, as we saw earlier. There are a number of ways, right? By making very structured, controlled scoring procedures for judges, and for example, with test administration, coming up with a structured procedure for the examinees to take the test. Okay. And the error is actually the difference between what you observe, right, the score, versus the theoretical sought after score, which we never really get, but we try to approach it as best as we can. Okay. Now, what is statistical regression? Or regression to the mean? You've probably heard this concept before in stats. Yeah. Well, it's the idea that in most cases, extreme scores, extremely high or extreme low scores on a test, if you measure that same person again, odds are the next measurement, yeah, and for an extremely low, extremely high score, they'll be closer to the mean the next time. They won't be as low or they won't be as high. Yeah. Now, why is that going to be the case? Probably be the case. Yeah. So what brings scores closer to the mean? Is it gravity? God? What brings the score closer to the mean? Alrighty. Well, it's probably neither gravity nor God. Alrighty. And don't confuse God with gravity because she or he really doesn't appreciate that. Alrighty. The idea with regression to the mean is that happens because every time we take a measure, yeah, it includes, going back to classical test theory, the sought after true score plus error. And the idea being that when you measure someone again, right, if the first time you measure them, they had an extremely high score or extremely low score, that the odds are, not definitively, but the odds are that there was an error, right? Or in the low score, negative error, and in the extremely high score, positive error. Alrighty. So what would be an example? Example would be, would be, let's say the test was how many shots from the free throw line a basketball player can get into the basket out of 10. Alrighty. So you get a bunch of HBU basketball players, and they all take 10 tries from the free throw line. Alrighty. Now let's just say one of the players only got 2 out of 10, and the other one got 10 out of 10. Alrighty. Now, odds are that the one who got 2 out of 10, I mean, maybe a crappy player, so it could be true, close to the true score. But let's just say everything being equal, and that was a low score, extreme low score of that, um, as a general matter for a basketball player. Okay, odds are there was some error that may have been introduced. Yeah. Now, for example, examinee error, right? Conditions, examining conditions it can introduce error. So maybe the night before, his girlfriend or boyfriend broke up with him. They're bumming out. They didn't have a lot of sleep. So on the day of the test, right, there's a lot of stuff that affected his or her performance. Right? And then for the high score, maybe they got a lot of sleep. They're feeling really good. They had practiced free throws every day that week for some odd reason. And boom, but that's an unusual thing, right? They don't usually do that. They don't usually get that much sleep. Right? But the odds are when you measure both players, right, a week later, right, the first one may not do as poorly as she or he did the first time, or the one who did extremely good, maybe she or he won't do as well the next time around. Okay, so that's the idea, yeah, because in classical test theory, there's always the truth score plus error, yeah. Odds are, right, the odds or probability suggests that the next time you measure it, then there won't be as much error, either negative or positive. Okay, now how high? Now, I'm not asking you how high you are now, if you're on a substance, if you're on some kind of illegal substance, I really don't want to know. What we're referring to here is how high should reliability be, alrighty? And that depends. It depends on the use of the test. That's one of the big considerations here. Yes, we talked about before, our correlations, there's the rule of thirds, but in terms of reliability, it kind of depends on some factors, one factor being on the use of the test. Right? So if the test is going to be used for an important decision, like let's say admission to a university, you're going to want high test-retest reliability. And that's what the SATs do perform, do demonstrate, yeah? They do demonstrate fairly high reliabilities in the 90s, all righty? That's why as a general matter, in the absence of really extreme circumstances, like you're sick as a dog the day you took the SAT, yeah? Presuming everything being equal, you prepared reasonably so, you slept your usual amount of sleep, nothing weird happened to you personally, and you took the test and you got a score and you're thinking, gee, I could have done better. Let me take it again. Is it possible to do better? It's always possible to do better. But the odds are, if everything's fairly equal, right, there's no extenuating circumstances, the odds are your score won't be that much better, higher or lower, because the test does demonstrate such strong reliabilities. Okay, that doesn't mean you shouldn't bother if you think you prepare a little better and get better sleep, or get a more focused. Sure, but in the absence of extenuating circumstances, odds are, that's all I'm saying, not absolutely, but the odds are your score won't be that different. Okay. If the test is one among a number of things, then you can have slightly lower reliability. So, for example, if a university doesn't just rely on the SAT, and most don't, most do take into account a number of variables like GPA, maybe an ACT score, ACT score, other circumstances. Then the test you can deal with more moderate reliability, like 85 to 90. And then finally, the author mentions that if it's going to be used for purposes of research, to determine group averages on different parameters, let's just say you're doing a drug study on depression, so you want to be sure your sample demonstrates a moderate amount of depression, then you can probably deal with a slightly lower reliability, probably between 0.80 and 0.85. I'm actually not exactly sure why the author takes that position, but that said, that's the position that the textbook kind of puts out there. So just wanted to lay out what the author is suggesting. Yeah. Maybe because arguably the test is not the focus of research. The drug and its impact on depression is really the focus. As a general rule of thumb, aside from the purpose of the test, high reliability is a 0.90. Think of it as an A. Moderate is 0.80, right? And 0.70 is low. Well, don't think of it as great, right? Because 70 is average. But 80 is moderate to high, 70 is low, and anything lower than 0.60 is unacceptably low. Low reliability. Okay, now, how do we determine reliability? All righty, well, there are a bunch of methods. Um, this isn't a whole lot of fun to go through, but let's go through it. We'll get through there. We'll get through it. All right, just um, give me a moment for a little Red Bull shot. Okay, mood improved. There we go. So, what are some ways to determine test reliability? How can you determine it by research? Okay, well, one is to simply do a test retest reliability. All right, so whatever test your test of anxiety, administer to a bunch of subjects, like 30, 40 subjects at one point in time, and then measure them again, let's say 5 days later, to see if their anxiety is about the same. Alrighty. Now, when you do a test retest, what does it essentially measure? Okay, it assesses for one. Let's just say you take scores, right? You get the samples 30 to 40 anxious people at point one, and it's the same bunch of people at point two. And let's just say you got a correlation of 0.85. Alrighty. So there's about a 0.15 that's unaccounted for. Alrighty. So what's that 0.15? You might be asking yourself, where's that error coming from? Alrighty. Well, it may be very well coming from the personal conditions of the subjects, right? Stuff that's happened to them. It may be due to how the tests were administered, but it may also be done due to scorer variation. Right? But if you had a very structured test, you administered it in the same way, right? It's probably due more to the first of the three factors. All right. So that's the way you do it. That's the way you could think about the score and what's going to that error. The other is interscore reliability. Okay, so this is another type of reliability where what you're concerned with is how well judges or evaluators or examiners or scorers score the test. Okay, so maybe it's a measure of depression that's done by way of clinical interview, right? So the person asks a bunch of questions, and then based on your response, she or he scores you. All righty. So what you would do then is you would get, let's say, two people, right? Two scorers, two judges, and they would evaluate the same subjects. All righty. And it very well maybe they're evaluated the same day. So subject goes to room A, is evaluated by judge A, and then goes to room B and is judged by score B, judge B. Okay, you probably have to mix up the order, right? Some people go to B first and then A. And then what you do, right? A is one variable, B is the other. They're two judges. You try to examine how similar their scores are. And what you want is a high reliability, generally, right? We want high reliability. But that high reliability will tell you to what extent you have interscore reliability or the judges, right? Based on how they use your test, right? And, follow the test administration, how well they can rely, how reliable judges will be. Okay, so it's not so much the test, but so much the judges, yeah? To what extent they're reliable using your test. Another way to find reliability of a test is to use alternate forms of the test. Okay. Now this is simply generating two forms of the same test. Okay. So let's just say you have a test of eating disorders. Okay. Now when you generated your test, very often a way tests are made is that people come out with an outline. They'll say, okay, looking at the DSM, right, there are these 10 major criteria, for example, and I need to ask a question from each of those parameters, right? Like, excessive exercise, over concern about body image, blah, 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 right? So 10 different things. So they'll write the questions in one way, right, using a Likert scale. And then they could generate another test using the same outline, but using slightly different wording, right? Have two forms of the same test, okay? Because you say a test should have these 10 things, right? You should ask them and then get a response on a Likert scale. But now you have another version of it, right? An alternate form, right, that follows that same structure. And essentially what you do is you give both forms to the same subjects and you see if they score similarly. Okay? They should score similarly if they're similar tests, but if there's variation, that might tell you something about the structure of the test or the wording of items and so on. Okay, if you do it at the same time, right, you get subjects to take version A and then version B of the test, right? We're looking at the test itself, our test content, and so on, right? It tells you something about how well you sampled um, items for the content, your content sampling, right? How did you collect and generate items for your test? Alrighty, but if you did a slightly different design, and let's just say you gave form A at one point, and then 5 days later gave form B, right? Because of that increased time interval, not only does your reliability index, right, or the absolute value give you some measure of content sampling, it also tells you something about the personal conditions of the subjects, which may vary across time because they're not doing it the same day. It may also be related to administrative conditions, right? Maybe you administered it differently at different points of time, right? You gave A in one way, and then you gave B in a slightly different way, all righty? But if you did administrative procedures similar, right, then odds are you're just looking at either content and or personal conditions affecting reliability. And that's what your 0.80, 0.85, whatever is telling you, right? That error is probably coming from how you word the items. Yeah, so that's important to know how much the wording of the items can impact things or versus the personal condition or the personal conditions of the examinees. Now, what is internal consistency? There are a couple ways to do this. One is with split half reliability, and that's simply with some tests, maybe literally in a very concrete way, splitting your test in half. Okay? So let's just say you have a long personality measure, and what's long? Well, let's just say you have something like 350 true/false items. That's a lot of items. Yes, and that's not uncommon with personality tests, which we'll get into later. Alrighty. But if you have something that long, what you can do is probably split it up into two tests of 175 items each. That's still kind of long. But now, right, you have two versions, right? Maybe you might take all the odd numbered items from the 350 versus the even items, and then now you have two forms, right? Odd numbered, odd item form, even numbered form. And then you administer it to the subjects, all righty? And if there's a high degree of internal consistency among the items, because the odds are when you have 350 items, you're going to be mixing up all different kinds of items throughout a test, okay? And if there's internal consistency in the test, split half reliability can show that. Yeah, if you have a high reliability between the test with all the odd items, for example, versus the test with the even items. Another way is by way of a coefficient alpha design, okay? In sum, what is that? That is a study where you give a test to a bunch of subjects, right? Let's just say it's an anxiety measure with 20 items on it, all righty? And what coefficient alpha does is that you can generate a whole bunch of correlations, right? First of all, the relationship of each item with the rest of the items. So you can see the correlation between item 1 with 2, 1 with 3, 1 with 4. And then you can see also the relationship of each item with the total score. So 1 with the total, 2 with the total, and 3 on. So you can see all kinds of permutations of item intercorrelations. Okay? And if you have a large degree of internal consistency, right, you'll have variations in all the different permutations of correlations between all the permutations of item combinations and their correlations right? So 1 to 3, 1 to 4, 1 to 5, and so on, and then 2 to 1, and then 2 to 3, 2 to 4. When you look at all those correlations, if there's high internal consistency, there will be relatively high correlations among all those different pairwise comparisons. Okay, so what are some examples of tests with good internal consistency? The SAT, yeah. Both the verbal and the math tend to demonstrate very high internal consistency. And just some general points with, let me just get back here, with internal consistency. The more items you have, the greater you increase reliability. All righty. So that's kind of a general rule. And that's why very often with well-crafted personality tests, they can demonstrate a large degree of internal consistency and high reliabilities as illustrated by by the research examples I just described. All righty then, starting to round the corner here. Another concept that's really important for our purposes, yeah, is the idea of standard error of measurement. Okay, now what is that? Okay, what that refers to is how a score can vary from the mean. All righty, it's so if a person were to take a test, how much can their score vary if they were to take it again? All righty. So related to that notion of reliability or consistency of test scores. Now, how do you determine the standard error of measurement, or SEM? Not standard error of estimate, right? We'll talk about that later, right? As it relates to homoscedasticity and heteroscedasticity. Here we're talking standard error of measurement, SEM. Okay, you determine it by, it's the product of the test standard deviation times, I'm sorry, this is supposed to be a square root, but I don't know how to do a good square root on PowerPoint. So times the square root of 1 minus the test reliability. Okay, maybe it's a retest reliability value that was found in a study of the test. Okay, and when you get that value, right, let's just say, we'll look at an example in a moment. This SEM is kind of a standard deviation unit, okay? And you would use that around the mean of the test. Right? So again, you would divide up the scores, the bell-shaped curve of scores, right, using the standard deviation unit. Here it's called SEM. You divide the bell-shaped curve into units of 3, right? 3 above the mean and 3 below the mean. And each of those units, right, or those 3 units above and below, is a way to talk about to what the standard degree, the extent to which the score can vary or deviate from the mean. It's like a confidence band, okay, to telling you how much that score can vary, can go up and down, okay, not the standard error of estimate. So same thing, use the bell-shaped curve. So 1 SEM, 2 SEM, and so on, 3, and same thing, 1, 2, 3 in the opposite direction. And then this will tell you that 68% of the scores, the next time you measure them, will fall one SEM this way, 1 SEM that way. 95% of the scores will fall 2 SEM from the mean and 2 SEM in that direction. All righty then. So let's just say a test demonstrated test-retest reliability of 0.75, okay, with a standard deviation of 15. What would be its standard error of measurement? Okay, so the SEM would be equal to the product of 15 times the square root of 1 minus the test-retest reliability, right? So that's going to be 15 times the square root of 0.25, 15 times 0.5, or 7.5. Now, what does so now we have a form of the standard deviation, but it's called the standard error of measurement. And this standard error of measurement this test has an SEM of 7.50. Okay. Now, what does that tell us? Okay. Again, using the bell-shaped curve, we can say, right, 68% or 1 SEM up and down plus 7.5 minus 7.5 around the mean, that 68% of the cases will be within plus or minus 1 SEM or plus or minus 7.5 around the mean. So if the observed score is 100, right, Tommy scores 100, in 68% of time, in 68% of all the possibilities, right, of Tommy retaking the test, there's a 68% probability that he will fall between 92 and 107. If that's his score, right, there's a 68% probability that if he were to retake it, that his score would be plus 7.50 or 107.50, or as low as 100 minus 7.50, 92.50. Now, so that's a big range, 92 to 107. Okay, and that's probably most people's experience of taking the same test again, right? Well, usually people tend to do better, right? But people can do poorer depending on various conditions. So again, like the variance, right? Let's look at two standard deviations, right? So it's two standard deviations, two SEMs, two standard deviations, or two standard deviations, or two SEMs, account for 95% of the scores in a normal distribution. So we can also say that if Tommy scores 100, we can know with a 95% degree of certainty, right, that his score will fall two standard deviations above and below, right? That's what 95% occurs. 95% accounts for is 95% of the scores within the normal distribution of scores. If you were to take a whole bunch, if theoretically, right, Tommy were to retake the test, let me take a step back, yeah, because if you took a test 100 times, you better be getting better at it. But just where his score, what the odds are, yeah, that's what, if you were to for what the this number represents is the probability that his score will fall two standard deviations either above or below. So that's kind of the window, the confidence span of where his score could fall. Yeah, here it says 1.96, but you can round it up to 2. So 2 times 7.50, that's 15, right? So Tommy's score will be about, well, if you use 1.96, but really 2, right? 2 times 7.50 will be about, could go as high as 115 or as low as 85. Okay, but you're 95% certain that this is where it can fall. Okay, you're 95% certain it'll fall in this range. So that's the idea. Yeah? So the SEM is like a form of standard deviation, and it allows you to predict what Tommy's score will be with a 68% degree of certainty or a 95% degree of certainty. All right, then, with that, we have another example, but I won't be going through that. And with that, that ends our discussion about reliability. Whew. Yeah, I know that was a hard one to trudge through, but we trudged through it. All righty. So with that, that ends our discussion on reliability. And with that, I will see you as we work on an exercise or two related to these topics. All right. Thanks for the privilege of your time, and I will see you in our next YouTube video. All right. You take care. Bye-bye.